Hello everyone, my name is Jie Zhang from KAIST. Today I will talk about our work, DRAMless, which is the hardware acceleration of data processing with new memory. The traditional heterogeneous system, which including the accelerator and SSD, can face great challenges. Here is the simple architecture of the heterogeneous system. The storage and the accelerator are discrete devices which are connected to the host. Before the accelerator can access data, we need to move the data from the storage to the host first, and then move the data from the host to the accelerator. During this procedure, the host needs to handle multiple software works. For example, we need to create a file descriptor for the read access. We also need to allocate the virtual memory and allocate the memory for the coprocessor. We need to request the file reads and allocate the physical memory. Afterwards, we need to generate the request for the data. Then the host can transfer the data from the storage to the DRAM and then transfer the data from the DRAM to the accelerator. Once the results are returned from the accelerator, the host also need to handle multiple software works. For example, the host need to request the file writes. It then allocate the physical memory and then copy the data. And then it will transfer the data to storage. Once the data transfer complete, the host also needs to release the memory and release the internal memory within the coprocessor. Afterwards, it deletes the file descriptors. To sum up, data movement in traditional heterogeneous system can introduce redundant data copies, software intervention, and the data transfer overhead. The data movement overhead can introduce huge performance degradations and energy cost. We compare the performance and energy of a heterogeneous system and an ideal system. We assume that ideal system has all data in the accelerator, which does not require data movement. As you can see from the left figure, the performance of heterogeneous system actually degraded by 38% compared to the ideal system. You can also see the energy consumptions in the right figure. Compared to the ideal system, the energy cost of a heterogeneous system actually increased by 5.2 times. To address the challenges, we propose DRAMless. DRAMless is a new accelerated hardware platform. It can eliminate the software intervention from the host, remove the data movement overhead, and can provide the environment for flexible computation. Compared to the traditional heterogeneous system, we introduce PRAM as storage media. PRAM can provide large capacity to accommodate all the dataset. Our DRAMless implement a real PRAM-based memory subsystem and integrate it in the accelerator. All cores in the accelerator can directly access data from the PRAM subsystem as memory. Next, I will talk about our overall design, including the hardware platform and the program model. Our accelerator platform includes 8 cores. 7 cores work as agent to process a kernel. The last core works as a server to coordinate the kernel scheduling. It also employs MCU to manage the PRAM access. All the cores are connected through a crossbar network. Our platforms include register sets to manage the status of the platform. It also includes a PCIe module to interact with the host. We also attach our PRAM-based memory subsystem to the crossbar network. They can directly replace the traditional DRAM. The figure is a traditional heterogeneous system that I mentioned before. In traditional heterogeneous system, the host needs to prepare both data and the kernel for the accelerator. This can introduce high system overhead, redundant data copy, and a long data transfer delay. As we can store all the data in the accelerator side PRAM, our DRAMless only need to prepare the kernel, which can simplify the whole procedure. So host firstly generates the compute kernels. It then groups the kernel into a package and download the package to the unused PRAM space. The server in the DRAMless will take over the remaining task. It passes the packages to extract the kernels and schedule the kernels to the agents. The agents will process the assigned kernels. Next is our evaluation. Our hardware platform uses 8 cores, each running in 1 GHz. The read and write latency of our PRAM bank is 80 nanoseconds and 10 to 18 microseconds. We use Polybench benchmark as our evaluation workloads. Our PRAM memory subsystem is shown in the table. We use LPDDR2 NVM timing diagram. We evaluate different potential accelerator designs. The first configuration is heterogeneous system, using the SSD and the accelerator as discrete device. We use SSD and the PRAM as a storage device. The second configuration is to integrate the flash-based SSD and the PRAM-based SSD in the accelerator. It still requires DRAM as a buffer. The third configuration is to integrate the NOR-based PRAM in the accelerator. The NOR-based PRAM is an old module of the PRAM. The last configuration is our DRAMless. We compare the performance of different accelerator configurations. We first compare the heterogeneous system and our DRAMless. Heterogeneous system suffers from the high data movement overhead, so it degrades performance compared to the DRAMless. Another comparison is the legacy PRAM and our DRAMless. Legacy PRAM employs the narrow interface for the communication between the PRAM and the controller. So legacy PRAM has much lower throughput compared to our PRAM sample. The third comparison is the integrated SCLC, MLC, and TLC. They still require to move data between the NAND flash and the coprocessor internal DRAMs, so it will take more time compared to DRAMless. We also compare the traditional SSD firmware with our FPGA-based hardware automation. The traditional SSD firmware introduces high overhead due to the low computation powers. Thank you for your attendance. I will take your questions.